Today we'll be doing section 9.2, measuring angles and arcs. So the first definition we're going to go over is a central angle, and this is an angle whose vertex lies at the center. So if I have a circle over here and I have a center point, I'm going to say this angle here, A, B, C, is a central angle. The next definition is an arc, and it has two endpoints on the circle and all the points that lie in between. So if I had on this example here, here's point A, point C, and then all the points in between would be arc AC. And when we write out an arc, we say endpoints being used just like we would a segment, but we curve the notation above to show it's an arc. And you can have lots of different types of arcs. We can have an arc from here to here. Maybe this is X and Y. And then all the points in between arc XY or backwards arc YX are the same arc. So there are three types of arcs. The first one is a minor arc, and it measures between 0 and 180. So it has to be bigger than 0 and less than 180 at the same time. It's also equal to the measure of the corresponding central angle. And then very important here is it uses 2 points to name it. So a minor arc will use 2 points. Let's say this angle here was 40 degrees. That would tell me that angle or arc AC is a minor arc, and it would also measure 40 degrees. And I would name it saying AB with the arcs above it. The next type of arc is a major arc, and it measures between 180 degrees and 360 degrees. This time it's going to use 3 points to name it. So sometimes we could have, say, an arc AC like I did earlier, or now I can have the same endpoints A and C but go this direction. See how this arc AC is much larger than my original one? So to indicate I want the larger arc, the major arc, I would need to use 3 letters. I would say arc A, heading in the direction of either Y or X, it doesn't matter, and then ending up at C. So 3 letters would show me to start at A, head towards Y, and then end up at C. That would be our major arc. And finally, my last type of arc is a semicircle, and it measures exactly 180 degrees, and it uses 2 points to name it, but also sometimes 3. So I can even add that in, sometimes 3 points, either or. Because it has to be through the diameter, so if I extend this right here over to X, I can see that AX is my diameter. So if I said arc AX, that would be the diameter. So that would be a semicircle. But using 3, I could also say A heading towards Y, ending up at X. That would be okay as well. The one you have to use 3 letters for is the major arc only. Okay, so now I have drawn some circles here, and I just want to point out what congruent arc looks like. Say, for example, I tell you my 2 green circles are congruent. I can say any one of the 4 arcs, AB, BC, CD, or DA would be congruent because they are all 90 degrees in the same circle. Or I can even go and say AB is congruent to arc EF or GH or HG in the circle to the right, because they are either in the same circle or congruent circles. Now, if you notice over in the pink circle, even though arc QR measures 90 degrees right here, the fact that it is in a larger circle tells me that they are not going to be congruent to the other 90-degree arcs. So that's what it is meant when I say same or congruent circles. Adjacent arcs, remember the word adjacent means next to, are going to be arcs that are next to each other. They have exactly 1 point in common. So you can look at any one of the circles up above that I have. I'm going to go with arc QR on the big pink one. So QR and RS would be adjacent arcs. The 1 point that they both share is the point R here, so they are next to each other side by side. And now my theorem 9.1 talks about what we have mentioned earlier. Arcs are equal to your central angle, so therefore in the same circle or congruent circles, two minor arcs are congruent if and only if their central angles are congruent. So we have to have those central angles are congruent. And again, we talked about how just because the central angle on the pink circle up above and the green ones are the same, the fact that they are not congruent circles won't work out. All right, the postulate 9.1 now says the measure of an arc formed by two adjacent arcs is going to be the sum of the measures of the two arcs. You can see I have a diagram here, so if I put A, B, and C, if I have the measure of arc AB plus the measure of arc BC, notice I'm still using that notation with the M, equals the measure of the arc A all the way to C. And again, if we had, say, if this was 90 here and this was 20, I could say 90 plus 20 would give us 110 for the arc AC. For examples 1 and 2, keep in mind a circle adds up to 360 degrees. So if I take all these central angles here, x plus the 60 plus the 130 degrees, all three of those angles has to make my full circle of 360. So since I want to find out what x is, I'm going to combine like terms and say 190 equals 360. We're going to go subtract that 190. And then I'll say x equals 170 degrees. So we'll stop right there for the x value. Same thing with number 2. The fact that I see these are congruent markings, I know that this is also 35. So I'm going to go all around and say x plus the 235s along with the 140 make my full circle of 360. Add those all up and I get x plus 210 equals 360. Subtract that 210 for a final answer. X equals 150. So all circles add up to 360 degrees. We can solve it by working backwards. Okay, in numbers 3 and 5, they tell me HK and G segments are diameters of circle L. Notice we used the center point to name a circle. So technically I would know those were diameters without being told because I can see those chords go through my center. I'm going to need to identify each of the following arcs as either a major arc, a minor arc, or a semicircle. And before I even do that, I'm going to go all around the circle and find the measurements here. So I see that 59 degrees, and then I see a vertical angle right here. I can make that a 59. And then here, well, along with the right angle and the 59 will form my semicircle, so I can conclude that will be 31. And then on the left side, I have another semicircle along with that 59 degrees, so that would tell me it's 121. Maybe that will help us when we do the examples 3 through 5. Okay, so the first things first, I'm going to go ahead and look at I, H, J. So it says starting at I, heading towards H, ending up at J. That is definitely going to be a major arc. The 3 letters kind of gave it away, but you don't know if the book's going to try to trick us by using weird notation. So now they say find that measurement. Well, it's all of the 360 except for the 90 I did not use, so that will be all of the 270 on the outside. So 270 degrees. So there's my answer for number 3. For number 4, they want to know what HI, so HI goes from here to here, which is definitely going to be a minor arc. And then again, the notation says you use 2 letters with minor arcs, and it will be 59 degrees since they are the same as their central angle that intercept it. And then I'm looking here at that last one with the 3 letters, so I'm thinking it could be a major, but let's go check. From H towards G, ending at K here, is actually a semicircle. And I did tell you that you could use 3 letters for a semicircle. So I'm going to go ahead and say semicircle. And we all know half of a circle will be 180 degrees. Okay, now the next definition is going to be arc length. There's a difference between the length and a measure. The length is the distance between the endpoints of an arc. So this is going to be measured in like feet or centimeters, but it's going to be the distance. So for example, what if I have a circle here at X? This could possibly be, say, a 60 degrees. The measure of an arc AB would be 60 degrees, but the arc length is the fraction of the circumference distance. So here is a formula I have for you to find the arc length. To find the arc length, we're going to say a fraction of the circumference. So in my example up above, that fraction looks like 60 out of the 360 possible. And then the circumference would be whatever the diameter might be times pi. So we would need some more information. But that's how you would find the arc length. I don't want the whole circumference. I just want a part of it. In examples 1 and 2, I'm going to start off by saying the length of that arc JK is equal to fraction times the circumference. And I can see that the radius is 2 feet, which would tell me the diameter is 4 feet. And I like to go ahead and use the diameter. The fraction I'm referring to is 30 out of the 360 possible times 4 pi, diameter times pi, and I'm going to put it all over 1. You could do some reducing here, but JK can be found in one quick typing into your calculator. Let's go multiply all the top numbers of the fractions. So we're going to say 30 times 4 pi. Hit enter and divide by that 360 on the bottom. So to the nearest tenth would be 1.0 feet. So that's the length of the arc. So again, the measure of JK might be 30 degrees, but the length is 1.0 feet. On number 2, let's go ahead and say arc length equals fraction times the circumference. And so we are looking for JK again, so this is the one right here, and the angle associated with that is 105. The fraction would be 105 over 360. This time they do give me the diameter as 15, so I'm going to go ahead and say 15 pi. And like I said, you can just grab your calculator and multiply the top. So 105 times 15 pi, enter, divided by 360, enter. The length here is going to be to the nearest tenth 13.7, and those are going to be in centimeters. So here JK is going to be equal to 13.7 centimeters. Once again, the measure would be 105. The length is 13.7. Two different measurements. So make sure you know what they're asking for. All right, this time they actually gave us the arc length in red, so we're going to work a little bit backwards to find another missing piece of our formula. So always start with your formula first. Arc length equals fraction times circumference. That way I know that the arc length is 7.94. Go ahead, put that on the left. And then I do know the fraction is going to be 70 over 360 times the circumference. And notice they want us to find the circumference, so they want us to find C. So I'm going to leave that C just like that. Let's go grab our calculator out and reduce this fraction on the right. 70 divided by 360. I want to turn it into a decimal. And I get 0.19444. Use as many decimals as possible. I'm going to actually use them all in a second because I'm going to use my calculator. To solve for the circumference, I got to do the opposite of multiplying, which is dividing. So divide on both sides. And then I'm going to type in 7.94 divided by, I'm going to use that trick to pull up all those decimals so I don't round too much. Hit enter. And our circumference then is going to be to the nearest tenth 40.8 inches. So they wanted us to find the circumference, which is C. We didn't even have to do anything about diameter or anything. We found it just using the formula. And then my last problem here, let's set it up. Arc length equals fraction times circumference. And if you have the formula written out first, you can make it easier to substitute where you need to. 1.31 is my arc length. The fraction is going to be the measure of this red arc, or the central angle. So I'm going to just say x for right now, x out of 360, because if I can find x, the measure of that central angle will also be the measure of arc CD. So then we're going to say times, right now I'm going to go right here and say the radius is 0.5. So if I double it, it would be 1. So I'm going to say diameter times pi would be 1 pi. Okay, we're going to go ahead and I'm going to go ahead and multiply over here. with my calculator. I like to just get decimals sometimes. On top over here, I have 1 pi on top, so I'm going to just go ahead and say pi. And then on the bottom of that right side, I'm going to divide by 360. And I get enter. So this one's going to come to be 1.31 on the left. And then here it was the decimal 0.00. Let's fix that. 87266. Try not to use too few of the decimals. And then that was times x because we had x on top. That way I can say divide by this decimal now, 0.087266 on both sides, 0.00872266. I'm going to use my calculator, so it's going to be 1.31 divided by, and I'm just going to pull up all those decimals like I've been doing before. Hit enter, and I get 150.1 when I round to the nearest tenth. So here is going to be 150.1 degrees equals x. And remember, if this central angle equals 150, then the measure SCD also equals that same 150.1. And that's what we are looking for. Okay, that's the end of my notes. So if you have any questions, make sure to find me and we'll clear things up.